Anyway, the problem is still, even we track the body effect of those transistors, but there is still some problem. I out is imprecise. Okay? Again, you need to know who controls the current ratio. Those two, right? But you can see that it is diode connected, and for this not. Okay, so you can see VT plus 2.2 VDS. So here only one VT, no VT, right? So minus 1 delta V. So you get 1.2 VDS here. But how about, right? Here is only this from here to there. And how about this? 1 VT plus 1 delta V. So the drain conditions are not the same. How to make this? How to make them the same? Okay, through the help of this one. See? We try to support both critical devices by the bias of the others. That's it. We can make them exactly the same. Okay? You can see here, 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 and there, right? For the main transistors and cascoding transistors, they don't generate the bias by themselves. Yeah, here it generates the bias by itself. Then they won't be matched. So the solution is to support the current controlling transistors and cascoding transistors with biases generated by the others. That's it. Piece of cake. But what is the problem here? Yeah, even though the expense is 4 extra transistors, that's not a big problem, because nowadays with new processes, the size of the transistors actually can be reduced much more than before. But from VDD to ground, you will see this, and that. They stack up to each other. It means what? The output string will be much reduced. The headroom, blah, blah, blah. Okay? Or the minimum supply voltage will be increased too much for new processes. So, how to estimate it? Yeah. What is the minimum supply voltage you need to have for VDD? Again, from here to there, 1 VD, 1 delta V, 1 VT, 1 delta V, and diode connection here, right? And the other delta V, okay? And then 1 VT, 1 delta V. So 2 VT, 2 delta V, and the other extra delta V. So totally, you have 2 VT, 3 delta V. Wow, that's too much. Okay, for example, this is 0.6, and that is 0.2. Right? Almost 1.8. That's it. Too much for new processes. What we can do is, this one is even more important for you. For in addition to regular cascoding, this one, low voltage cascode or high strength cascode, that is really, really important, especially for low supply voltage. Okay? But how to make it? Yeah, this is the very important structure for you. I hope you can memorize it. Okay, because for regular cascoding, you can see, yeah, right? I'm here. For example, here. How to generate the current, the bias voltage? Yeah, you need such kind of diode connection. Okay, so usually we have for cascoding, right? That is the usual case. Yeah, I need bias. Who supply me? My partners. For cascoding transistor, it also needs bias voltage. Who support it? Again, its partners. But by such kind of traditional cascoding, I told you already, the voltage here needs to be 1 VT plus 2 delta V, too much. Okay? So how to reduce the supply voltage requirement? Low voltage cascode will be the best solution here now. Okay? Again, see? How to generate such kind of bias, self-biasing, right? It can generate its own bias, but it doesn't have any kind of diode connection. No. The bias actually is connected to the top of your cascoding transistor. Wow. Wow. Okay? So what is the major difference? In the past, if I would like to generate my own bias, I connect my gate to my own drain, right? But right now, it is connected to the drain of its cascoding transistor. That's it. Okay? So, what is the minimum voltage here? Again, 1 VT, 1 delta V, right? And how about the regular cascoding? 1 VT, 2 delta V. Yeah, we set 1 delta V. We reduce the voltage requirement by 1 delta V instead of 1 VT. Sorry for that. Okay? Yeah, to be honest, not much for improvement, but it still has some. Okay? But it has a lot of constraints. Even though till now it is the best, the easiest, and almost the best solution to such kind of low supply voltage condition, but it has quite limitations. Okay? So, again, M3 and M4 need to operate at saturation. That is really important. How to make sure they operate in saturation? Okay, you see, for M4, node X of the drain needs to operate in saturation region. Okay, so according to VB, it cannot be 1 VT H lower. But the voltage actually is connected to here, okay, to M3. So you have 1 VT, VT3, and delta V3. Okay, so VB needs to be, how can I say? It cannot be larger than this one, node X voltage. The gate voltage of M4 cannot be 1 VT higher than the drain voltage. Cannot be. Okay, so it should be less than or equal to my own node voltage plus 1 VT. No much higher than that. Okay? Okay? And then you say, hey, I have some kind of upper limit. So I try to go downward. How low you can go? Don't forget, here, 1 VT, 1 delta V, and there, 1 delta V here. Okay? To make yourself on, your voltage needs to be 1 VT and 1 VTH higher than this. That's it. I need to be 1 VT, my own delta V, higher than that. That's it. Okay? So, that is the main limitations for you too. The upper limit and the lower limit. If you look at the content, what you can see? 1 VT, 2 delta V, right? Right? And how about the upper limit? 2 VT, 1 delta V. Okay? So here, 1 VT, 2 delta V. There, 2 VT, 1 delta V. So, what is the difference? VT minus delta V. Okay? Between the upper and lower limits, only 1 VT minus 1 delta V. VT, again, for 0.18, maybe hundreds, 5 to 7. And how about delta V? 2 to 3. Hundreds of millivolts. So the difference, again, only a few 100 millivolts. Okay? 2 to 300 millivolts. Wow. It means what? For such kind of low voltage cascode or high strength cascode, the bias for M4 is really hard to design because the tolerance is only 2 to 300 millivolts. And you need to be careful because for your first design, usually for TT, right? How about the other 4? FFSS, SF, anyway. And how about the temperature, right? Sometimes you design good enough conditions for TT, but for the other conditions, yeah, it doesn't work at all. All right? My own supervisor in the past, more than 20 years ago, Professor Liu, the best analog IC designer, analog IC design professor in Taiwan, he required us for chip fabrication, at least we need to pass 3 for post simulations. Okay, for post simulations, among 5 corners, we need to make 5. Anyway, my recommendation is to make sure nothing will go wrong. Not only for TT, that is the usual case, TT at room temperature. Okay, I hope to check whether or not it will survive for any kind of process variations. 2 extremes you need to check. The fattest at lowest temperature. Lowest temperature means it's up to your application. Okay, for commercial chips, maybe 0 to 70 or 75. Okay, for military applications, to my memory, minus 25 to 125. That is to my memory. But for temperature sensor, usually we have minus 40 to maybe 150. Blah, blah, blah. Okay. Anyway, FF at the lowest, for example. Okay. The lower temperature means the faster speed. That is the usual case for our semiconductors. Why? Because higher temperature means more vibration for the lattice. It is harder for the free electrons to penetrate through the lattice. Okay, so the higher temperature, the lower conduction. That's it. Okay. So. Again, you simulate under such kind of condition, right? So to the fattest condition, FF at lowest temperature, and the other extreme condition, the slowest. Okay, that's it. SS at the highest condition, the highest temperature. If it can survive, I think no problem at all. Okay, under such kind of 3 conditions, I promise you, it will function. You don't need to check for all the others. Well, those 3, good enough. So first cut at TT, room temperature. Okay, then check here and there. For such kind of very easy circuit, if you cannot survive, please leave the class. Please leave analog IC design. Okay, piece of cake for you. Yeah, just check it. So, with the help of low voltage, high swing cascode current source, here we make it. Okay, that's it. Again, you can see The Cascode, the bias actually is automatically generated by such kind of connection, but not to its own drain, to the Cascode, the drain of the cascoding transistor. Okay? Yeah, and then you can see, wow, you can see M3 and this, perfect. They have the same, because the bias is generated from here, right? To supply M3 and this one, and M4 and the other one, their bias is generated by the others. So the condition, okay, you can see they have the same gate voltage. So 1 VT, 1 delta V lower, 1 VT, 1 delta V lower. Congratulations, your drain voltage and my drain voltage are exactly the same in theory. Okay, and how about our gate voltage? Automatically generated by such kind of connection. We have the same gate voltage. We have the same sort of configurations. If they are the same, then I out and I reference will be exactly the same in theory. Okay, and how about the minimum supply voltage? You can see it is connected to X, to node X, right? So 1 VT plus 1 delta V, right? Here, over there, only 1 VT plus 1 delta V. But how about I reference? I reference usually behave like this. So 1 delta V, configurations, 1 VT and 2 delta V. Okay, we can make it. Yeah, and how about the original one? Oh, see, 2 VT and 3 delta V. Right now, we reduce it through the help of low voltage cascoding. We reduce it from 2 VT plus 3 delta V to 1 VT plus 2 delta V. Excellent. Okay. The supply voltage can be much higher than this through the help of low voltage or high shrink Cascode. But what is the price? You can see totally for such kind of simple current source, we need 10 transistors. It's up to you. I have no bias. Okay, it's up to you. Yeah. Again, nothing is free. You need to pay for it. To get accurate enough, right? And also, you can see here VT plus 2.2 delta V, right? So what is the output swing? What is the headroom? Sorry, know this and know that. Okay, 1 VT and 1 delta V lower. So the minimum is 1.2 delta V. Wow, excellent. You have very small headroom. You have cascoding. You have very high output resistance. Okay, and also the supply voltage, is not as high as before. Perfect, but you need 10 transistors, as you like. But to my own experience, usually we don't apply this because it's too hard to design. Current source is only one of the building blocks of your huge analog chip. Okay, if for such kind of, you have maybe tens of current sources required, for each one you need to apply such kind of very complicated structure. It will make your analog IC design much more difficult than before. So to be honest, the most popular, okay, the most frequently used current source is the simplest one. What do I mean? This one. Never mind how many circuits you learn, how many structures you learn. To the end, usually the simplest is used. Okay, but through such kind of teaching process or learning process, you know a lot of fantastic skills. For example, low voltage or high shrink Cascode. Sometimes when you have problem with your low supply voltage, you need to think about this. Okay, that's it. So the most important lesson for you is to get some kind of understanding, some kind of memory about such kind of very important structures. Whenever you need, go back to your slides, go back to your textbook to check the detailed circuit. That's it. Okay. Maybe sometimes you need this. Very low, very small headroom, high high accuracy for the current ratio, and again, low supply voltage. If you need 3 extreme conditions, please memorize this. It will solve your problem in the future. But usually we don't apply it because too expensive, too hard to implement. Okay? Only when necessary, but when very, very few. Okay? Very unlikely you need such kind of very expensive circuit. And then let's go for the others. Supply independent biasing. Yeah, that is almost to the end of this chapter. Yeah, what we care about current biasing is if I would like to generate some kind of reference current for you. By definition, if you would like to be a reference to the others, you need to be standardized. Okay, it means what? Never mind under what kind of condition, the current should be unchanged, should be fixed. Okay? But it's really upset that you can see from all the circuits we teach you, the output current will be changed according to supply voltage. The higher supply voltage usually means what? The more output current. Okay? Even with this. This is VDD, right? If you increase it, forget about it, I promise you, all the currents will be increased. So the same, your output will be also increased. It doesn't make any sense. To be a reference, you need to stand still. Okay, I'm such top. Never mind what happens to myself. I don't bend down. That's it. I provide a standard reference to the others. I don't change my value, my amplitude under any kind of situation. I mean temperature change. I mean supply voltage change. No. I need to stand still. I don't change myself. So how to generate supply independent bias? It is really important for some applications. Okay, especially for commercial chips. If they told you, oh, it can operate under 1.5, 1.8, 2.5, 3.3, usually the tolerance is positive, negative 10%. Okay? Then what will go wrong? For example, with such kind of very easy reference current for you, you can see, I reference, okay, very simple derivation by yourself. But I would like to say that, if the voltage, the supply voltage is increased, then the so-called reference current will be increased by 2 order. Okay, yeah, by squared. Okay, instead of only 1. Yeah, it is not only proportional to the magnitude of your supply voltage. No, to the square of your supply voltage. So if you double your supply voltage, then in theory, I reference will be increased by 4. In practice, more than 4, because this is not 0. Okay, I promise more than 4, much higher than 4. So it is supply dependent. Okay, that is no good. How to make your supply voltage, your supply current, independent of the supply voltage? We have 2 major categories for you. Through the help of VBE or through the help of VTH plus self-biasing. Okay, for example, VBE biasing circuit, just like here. Yeah. For derivation, you can see VBE here, right? And then how much current will flow through RS. Piece of cake, right? VBE by RS, that's it. Okay? Yeah. And then how much current for IO? Yeah, here and there, but usually if beta is large enough, you can neglect it. Okay, so this is some kind of rough estimation. Not accurate. The rough estimation, it looks like this. Anyway, never mind. You count this or not. I don't care. I don't care. Okay? I would like to tell you that where is VDD? Nothing. No VDD in the equation. But you have V plus minus V minus. If this is 0, then we will call it VDD, right? So this means VDD. VDD exists in the equation, so it has quite much impact on the output current. But here, please tell me, where is VDD? Nothing related to VDD. So in theory, never mind how much VDD you apply. Yeah, it doesn't matter the output current at all. In theory. How about in practice? A little bit, but not much. At least much better than this. Much better. Okay? Congratulations, you make it. This is the supply independent bias current. Okay? But it still have the other problem. You can see, never mind VBE or VTH, it is proportional to VT. Thermal voltage. What do I mean? Okay, not threshold voltage. No, I'm talking about thermal voltage. Thermal voltage, it means what? The magnitude is directional proportional to your temperature. I mean in absolute temperature, degree scale instead of Celsius or Fahrenheit. No, I'm talking about Kelvin temperature. Okay? So, even though it is not in supply voltage dependent, it is still temperature dependent. Okay? Yeah. How to make it both supply voltage and temperature independent? Yeah, that is another story. Much more complicated than what I would like to teach you in this chapter, because this is the first chapter I would like to teach you about circuit design. Before that, all about devices. Okay, so I wouldn't like to make you upset. To make you feel comfortable, then we go further in the other chapters. I mean, we will focus on more complicated circuits in the future. Okay, yeah. Anyway, it is fairly independent of VDD, but you need to have such kind of BJT. For CMOS process, again, we don't have BJT transistor, but we have parasitic BJT, right? According to parasitic BJT, the beta is not so good. Usually only 10, about 10. Then it means what? The impact of such kind of current is larger than real BJT. It means the equation is not so accurate. That's it. But again, it's still VDD independent. Okay? Oh, another story for you. Another question for you. Right now, IO goes through M2, M3 to IS, right? How to supply such kind of reference current to the others? Come on, somebody. Anybody? Pardon? Yeah, exactly. Exactly. John, you're really smart. Yeah. When I was yeah. Exactly. Okay? That is the correct answer to this. How can you supply your I/O, your reference current to the other circuit? Don't be silly. Hey, look, I tap out. Oh, no, 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 no. After tapping out, the condition will be destroyed. Okay? So, what John said is a standard process for you to duplicate such kind of very good current. Okay? Through what? Again, current mirroring. In such a way, you can see no disturbance. Never mind how many you would like, maybe only 1 or 2 or 100, I don't care, because all those are connected to the gate. They don't have any kind of disturbance to the main current flow here. So it means what? The equation is still valid after you copying the current out. Okay, but for new engineers or new students, many of them would like to tape out from here, from there. No. According to KCL, okay, if you tape out something here, over there, the equations will be destroyed. It won't be valid at all. And I promise you, it will become supply voltage dependent again. Okay? Because for the circuit you tapping them out, usually their operation depends on supply voltage. If this or that is supply voltage dependent according to KCL, the final current will also be supply dependent. Okay, that's it. Yeah. That is also a very good, very important idea you need to know. Okay, but if you ask me, hey, this is for I reference, right? How about V reference? How to duplicate, how to tape out such kind of reference voltage output? Directly taping out is good enough. Because you tape out any kind of voltage, again, to the gate of the other. Who cares? Right? It won't destroy the operation conditions. So to tape out reference voltage, directly taping out, good enough. But for current, no. You need mirroring, current mirroring for help. Okay? So this is the reason why, if your teacher is good enough, he or she never asks you how to get V out. CD question. Direct tape out. Good enough. Okay? Yeah. And then if you see, it depends on you see I1 and over IS, right? I1 is for, how can I say, for MOSFET, and IS is for BJT. It's really hard to match both of them. Really, really hard. I told you already, you can only match the same device to the other. Okay? Yeah, you can match only exactly the same devices. Or more specifically, you can only match the same parameters. You cannot match, how can I say? Oh, my GM, even for MOSFET, my GM to your G out. No. They belong to the same MOSFET. You cannot match this to that. No. You can only, again, you can only match the same parameters of the same devices. Okay, that's it. So you cannot match the current for this and the current for that because one is MOSFET, the other is BJT. What we can do is this one. Okay? Yeah, one BJT and BJT there. After very simple derivation by yourself, piece of cake, okay? Let's look at the final result. Oh, bingo! Because they are of the same transistors, they are of the same devices. We can match this to that, but we still need to do good enough layout. For example, usually we have 1 to 8. Why? Oh, you're really smart. Yeah. 1. Okay, that's it. First order common centroid. Okay, 3 by 3. 9 transistors, 8 for this, 1 for that. That's it. Okay. If you look at the papers, it has very weird design. For example, 1 to 5, or 1 to something. Yeah, 1 to 5, it is still possible, right? Oh no, 1 to 5, no, it is impossible. It's really hard to have such kind of common centroid layout. 1 to 4 is possible. Why? Because you have 4, 4, 1, 4, 4, right? But this one is 2-dimensional common centroid. It is better than this, 1-dimensional. Okay? More symmetry, the better. The more symmetry, the better. Okay? And this is the reason why, if you look at the voltage reference paper, reference current paper, usually if they have such kind of BJTs, 1 to 8 is some kind of common sense. But what? You need to know. Okay? Anyway, right now we are really happy because we can match this to that in theory because they are of the same BJT. And also, you cannot find VDD here, right? So they are rather supply voltage independent. But you can see, KT over Q means what? Thermal voltage. That is moments ago what I mentioned. Okay. So the I/O is still directional proportional to your temperature. For a very good reference current, it still doesn't make any sense. It needs to be independent of not only supply voltage but also operation temperature. But how to make it? Yeah, today I wouldn't like to teach you about that. Too complicated for you. Now let's finish this chapter. Yeah, within minutes. CMOS peaking current source. That is another idea to make the output current independent of the supply voltage. Yeah. For derivation, I think that is really complicated, but by explanation, good enough. Okay, from the very beginning, if no supply voltage, no current at all, right? After you increase the VDD, finally it gets some large enough voltage for your M1. Finally, you will make it. If you increase VDD from 0 to something, okay, finally you will accumulate large enough voltage to turn on M1. So you can see, from 0 current all the way up. Okay, but be careful. From the very beginning, M1 operates in weak inversion region. From cutoff, weak inversion, then strong inversion, right? In weak inversion region, the current right, look like this, exponentially increased. That's it, the current. But what is the problem? Because the current will be increased exponentially, right? So the voltage here, the voltage difference will also be increased exponentially. Okay? So the current, that's the same. Yeah, because, okay, sorry. Again. You can see, what is the node voltage for M1? Actually, it becomes VDD minus I by R2 bar. But I increase exponentially. So after some time, this one will increase too fast. And the voltage will go down, okay? Yeah, from the beginning goes up, but too fast increase for your current here, right? So finally it will go down. Never mind for this one or for that one. Okay, so what does it mean? The current for your I out, from the beginning, zero, right? And after you get enough current, enough voltage here, it will conduct some current. So after some time, it will accumulate good enough voltage to turn on M2. But as I told you already, the current will be increased exponentially, right? So after some time, the voltage will reach the maximum and go down, okay? According to such kind of exponential increase. All right? So the final output will look like this, then go down. You have some kind of peaking. That's it. But how to derive it? I promise you, very complicated. Yeah. If you have time, please try it by yourself. I never derive it. I only explain the idea to my students. Good enough. Again, rough estimation. Okay? According to weak inversion, operation for M1. Oh, that is the key point. Okay, you need to design M1 operate in weak inversion. And the exponential increased for the current will stabilize. Yeah, we'll let the gate voltage on M2 have some kind of peaking, then go down, right? So the output current will look like this. Doing, doing, doing. But even with the same R2, okay, if you fine-tune your R1, you will see the peaking happens at different positions. So, as I mentioned, for your chips, 1.8, 1.2, 2.53, I don't care. You can tune the ratio between R1 and R2 to make the peak around your supply voltage. As you know, what is the definition for peak or valley? The slope needs to be 0, right? Right? 0 slope means what? Almost no variation. Even if your supply voltage is changing, no much variation for the output current because the slope is 0 for the peaks. Okay? I'm happy? In this way, we can make the output current quite independent of the supply voltage. But again, even though it is stabilized, the output current is stabilized around your supply voltage, but it is still very temperature insensitive. Okay? So to the end of the chapter, we wouldn't like to talk anything about how to stabilize the operation according to temperature variation because it is some kind of harder problem to solve. So we will face it in the future if we have time. Okay. Finally, I would like to tell you the other even good thinking about such kind of peaking current source, double peaking. Okay? Yeah. You can see here, if you have patent for this, how can I break through your patent? I change this. With what? The other one. Okay? We replace R2 with the other counterpart circuit. What is the definition of counterpart circuit? I told you already. Flip it upside down of anyway. Okay? Then change VDD to ground, MOS to PMOS, blah, blah, blah. Okay? Why we need to replace it? Because, again, according to the exponential increase of the weak inversion operation, we can have some peak for this one, right? If you flip it from N type to P type there to replace R2, it will have the other peak. If you design the ratios here, and you have R1, it has R2 and the other supporting transistors. The peak value for this and the peak value for that are different. Oh, congratulations. You have the first peak, for example, for N, and the second peak for P. Finally, the current will be stabilized in such kind of very wide region. Get it? That is a very simple idea by explanation. But for derivation, it takes hours, I guess. Usually it takes hours for nothing. You cannot derive the final equation, but through explanation, yeah. For MOS, you design your peak here, because you can see, I have my own R, you have your own R, right? Rn and Rp, you can fine tune the value, R and Rp, to have different peaking. Okay, here and there. Then for this wide region, the output current is quite supply voltage independent. Not exactly supply voltage independent, okay, but quite rather independent. Okay, anyway, anyhow, yeah, that is for peaking. Any kind of derivation, forget about it. Too complicated. Okay, yeah. How about MOSFET? You can see almost the same. From BJT, I mean here, right? Oh, there, BJT and this. Similar condition, similar operation you can have for MOSFET and that's it. And you can derive, and finally you have this. And again, VDD is not in the equation. Congratulations. It is supply voltage independent, roughly speaking. Okay, but you still have this. Again, the output current is temperature dependent, strongly dependent on operation temperature. Okay. Anyway, for such kind of MOSFET current sources, usually the output current can be from narrow ampere all the way to micro. We seldom design any reference current as large as milliamperes, but because it's too power wasting. Okay, if you would like to design your output current for such kind of very small operation, yeah, only narrow amperes, it can reduce the power consumption substantially. Okay, that is the key for very low power circuit design. It's really hard for you with bias voltage, yeah, to control such kind of extremely low power consumption. But for bias current, piece of cake, we can make the output in such kind of region. Okay, never mind. They operate in weak inversion, strong inversion, or even in with leakage current. Okay, it is totally possible. Yeah, to make the power consumption really, really small. I told you already, low power consumption and low voltage operation, they are totally different for circuit design. And this is really good for low power consumption. With bias current, you can make it easily. Okay, that's it. That is the end of the chapter for current sources. Then we go for the other, even more important chapter for op-amp. Op-amp is the building block. Op-amp is the building blocks for almost all the analog IC design. Okay, but why we don't teach you from the beginning with op-amp? Because inside op-amp you need current source. So we teach current source first, then go to op-amp. All right, let's have a short break right now.